learning all sorts of stuff about Linux.
Hi everyone, this is basically a pretty high level talk just about booting Linux, really. It's for people who know nothing about it and some people who know a little bit and just want to know a little bit more. It doesn't go into great detail except for a little bit at the end, which is like an exercise for the reader. So I'm going to basically cover a little bit of history and background of what booting is, typical boot process of Linux, a couple of bootloaders, CFE and U-boot, have a look at a real device, a Raspberry Pi, have a look at some of the kernel command line options you can use to make it behave differently, and that sort of thing. So, what is booting? It comes from bootstrapping a system, and it literally comes from the saying you're lifting yourself up by your own bootstraps, which I presume is an American because we refer to them as laces. You start a system, you've got software that has to run. How do you start that software? Well, inevitably you end up needing other software to start that software, so how do you start that software, and so on. So it has to start somewhere. In the early days, you toggled it in on the front panel using switches. I remember programming, I'm older than I look, I remember programming Altera 8800, and I had my piece of paper with my 5 instructions that I had to toggle in with 8 bits to put into memory and do that latch, that latch, that latch, and then at the end you could hit the run button and it would run them and actually boot the system. Of course you get it wrong, and you have to do it again. So in the 80s they stuck everything in ROM or EEPROMs into the computer, so all the C64s and the VVCs and so on. They're all in there, but once it's in there, it's stuck, that's what you've got. So now we've got flash and multi-stage boots and so on. So Linux. There's usually 2 bootloaders. On a device there might be several bootloaders, but there's a first stage bootloader which basically gets the system to a stable state, and then that's quite often these days programmed into the system on chip on a device by the manufacturer, or at least one time programmed on the production line. So in the Pi, Broadcom stuck it in there. Somewhere inside there, that big chip is Broadcom's little tiny initial loader. Then that goes to some sort of storage device, usually a flash chip or something like that, pulls in the second stage loader, and then that can pull in from a hard drive or another storage device or the same storage device, the actual kernel, and then the kernel mounts a file system off another storage device, and we're running. So, first stage bootloaders usually pretty simple, but technically the BIOS in a PC is a first stage bootloader, and that's not very simple. Initializes the hardware to a known state. It's basically there to get the second stage bootloader going. Usually from the manufacturer, because it's pretty hardware specific, and storing non-volatile memory. So yeah, quite often modern chips there's a bit of ROM or programmable memory in the chip, and once it's programmed, it's programmed. So we go back to these system on chips and so on. I work in digital television. For some reason all the TV broadcasters don't want you stealing their stuff. So the hardware has to be protected so that people can't reprogram them or hack them. So the way they do it is they sign all their pieces of software all the way through, so it only runs it if it's got the right signature. But the weak point is right at the start. So there's an encrypted memory on the SOC, which is already programmed and you can't change. And that's your first stage bootloader. Second stage bootloaders, quite sophisticated. you can have a command line in them, right? So you've got things like grub, CFE, U-boot. You can configure them, you can change them to boot different systems, different operating systems. Might have USB drivers in there and all sorts. So they are a lot bigger than the first stage bootloaders. So let's look at one. CFE, Common Firmware Environment, developed by Broadcom but is open source. It might have actually been developed by MIPS, but Broadcom kind of own all the IP, so they currently look after it. It's mainly on MIPS, but I have seen it on ARM, and I've also seen it under a different name, which I probably can't tell you at the moment because of NDAs and so on. But it's basically the same thing. The source is out there, so you can get it and recompile it and modify it and so on. And it's in a bunch of things: the Apple Airport, Linux modem, smart tellies. So you've got a Samsung Smart TV and you can work out where the serial port is. You might get to a prompt, you might not. It's got a serial console and command line. You can tell it to run any piece of code by just providing the address. You've got environment variables that you can program up so you can make macros. These can be stored so you can reboot. Like the special one is a start variable, so if you set the value of that, whatever's in that gets executed on boot. We've got networking support. So we can configure an Ethernet device. It's got a DHCP client, so you can get an IP address, or you can use a fixed one. You can ping to make sure it works. You can TFTP a kernel directly into RAM, so you don't. So apart from the bootloader, you do not need anything else on the system. And we can access various storage devices with it. So flash file like something like JFS2 or MMC or FATX2 or whatever. U-boot, very similar, used a lot more. Sources out there, people fork it. There are currently 3 different versions of U-boot on GitHub for the Raspberry Pi, all in various stages of disrepair, so to speak. Was originally developed for PowerPC, now near enough on everything. It's GPL2, but because there's you need to kind of, you don't want to actually have to kind of GPL everything you run on it. It's got a very specific exception in there so that when you call to run something, that doesn't GPLize the thing you're calling to run. So yeah, very similar to CFE. More use, more developers, more stuff in it. Serial, console, command line, run just as before, specified address, environment variables. It can read script files. So you don't have to kind of type everything into one line and try and fit it into a variable and stick it in, program it in V. You can actually write sensible little scripts and store them in the root of your, where you stored your U-boot. Network support, as before, storage style support, but it can do a lot more different file systems. USB support, which is kind of useful on a Pi, because networking is actually a USB device. If you can't support the network, so back to CFE, CFE wouldn't actually be able to network boot, not because CFE can't support network booting, but because basically you haven't got a device driver for the network on a Pi, So let's look at a specific project, and I am whizzing through this a bit as a request. The Pi. When you turn on a Raspberry Pi, the ARM has not started. The ARM is in reset, and it stays in reset for a little while. So the first thing that starts up is a GPU core. And Broadcom have stuck a first stage bootloader in the system on chip that's run by the GPU core. That kind of gets everything a bit stable, sets up your memory timing and so on. And then goes off and reads the second stage bootloader from the MMC. That's why you always need the MMC in a Pi, or the SD card in a Pi, because that first stage bootloader always looks at it. There is nothing else, it can't do anything else. It loads it and it looks for a specific file with a specific name, bootcode.bin, which is the second stage GPU bootloader. Now it does a bit more configuration, and it reads style, which is actually the GPU firmware. But as a side effect of the GPU firmware loading, it can go off and load the kernel. So what it actually does is there's a couple of text files in the root of your MMC. There's a config.txt, which if you actually look at the default one, everything's commented out, but it allows you to tweak some of the GPU settings. And there's a command line.txt, which I'll talk to you about in a minute. And that has all the kernel configuration options that you can tweak on the command line that are useful to the Pi. And then finally, it reads the kernel and runs it. You can actually, using config.txt, change the kernel name and get it to boot other stuff. And I'll show you this a bit later on. So, that, which doesn't fit very well on the screen, it's alright, the next slide has got it clearer, is the contents of command line.txt. And they are kernel options that are part. And if you stick your SD card into a PC, you can edit that and add them and take them away and whatever you want. So, for example, you can change the data rate on the console, or you can have 3 partitions on your SD card and change it to boot from get the file system from the 3rd partition. Maybe you've got 2 operating systems on it. So let's go through them. The first one is a bit hardware-y specific. It's very Pi specific, just disables the power management. Then we set up the serial port, the console. So we've got the console. The console actually comes out, that 10-way header, or whatever it is, I can't remember how many pins are in it, 20-way header, has a couple, an RX and a TX on it, which is the serial port. And if you actually connect a TTL level serially to the Pi to that, you can see all the kernel output coming out on that as well as on the screen. That's what that first bit does. You could set that to be a USB serial device, which could be useful. The second one is the virtual console, i.e. the screen, the frame buffer on the HDMI. Then we've got the next 2 are to do with the file system. The first bit is the actual storage device, so it's the second partition of the MMC. And the file system, it's an X4 file system. Then we've got something to do with I/O scheduling. That basically is make sure that the I/O is responded to in a timely manner. It's not real time, but because the Pi is quite slow, it just basically ensures that we don't let any devices hang a bit. And then the last one basically says, if I can't find my file system, I'm just going to keep looking. Normally what happens is, after if it doesn't become available immediately, your kernel panics. You get a kernel oops about a missing file system. So, a bit of detail about each of those. Consoles, where the kernel puts its output, can be overridden in the init process. So you quite often have the kernel we've got devices where the kernel comes out on one port and then everything's started up and the shell's actually on another serial port. Because the init process has run the Getty on a different port. Configured using the console options. We've got the default console, as I said, you could use a USB one. On a PC, You can use TTYS0 with, I've got an old-fashioned tin box one which has actually got a serial port on the back of it, which there aren't many of them around anymore. So that's the ARM. The AMA is actually the ARM serial device. So you might get other manufacturers who've got a custom UART as part of their chip, have their own custom driver, so it might have a different game. You can actually configure the network during boot, which is kind of useful. You use the IP option. Why do you want to do this? The kernel can actually mount a file system that's on another machine via NFS. In our development at work, we do a lot of stuff where we build everything and keep the root file systems on our development machines. And all our device has on it is the bootloader. So if we remember going back to CFE and U-boot on the fact that we could TFTP a kernel and run it, the kernel's pulled off of our machine from the TFTP server, that runs up, and then it mounts the file system that's also on our system, which means that we've got full control over it, easy to rebuild, we don't have to reflash or anything like that. And the only thing stored in the device is the bootloader. Okay, you've got a time issue, so sometimes you don't want to do it because NFS is not as fast as using a local file system. So yeah, root FS. So the root option defines the root FS. We've got a bunch of things there. Root flag. So if you're doing your mount and you've got the O option that you use, you need to put in special file system, Linux file system mount options. That's what root flag's for. Root FS type we've already seen, so that could be a file system type. There is a table of default file systems that a kernel will work through, which is like FAT and X2 and so on. NFS root, well, that sounds obvious. NFS root basically it's where it's the IP address and path on the remote server, and root weight we've already talked about, and there are some examples. So that one, which you can probably, I'll put these slides up somewhere so you can look at them afterwards. So lots and lots of options in this. It's alright, somebody's showing me a clock, so I'm going to speed up. Final one, you can put U-boot on a Raspberry Pi. Still a bit experimental. As I said, there are 3 different forks of it, and all of which work reasonably well. I have not successfully got it 100% working right. I have a Pi with it on, but it still has tweaks, and I shouted it. The loader passes all the kernel options rather than the command line.txt, but it allows you to have a whole bunch of kernels on your things if you're playing about with some extra hardware drivers and so on, enable them, disable them. The best of the bad bunch is that. You can build it for B at the moment with that. Save as the U-boot image to your FAT. Get rid of your old config and add one line to your config file, and that will actually tell it to boot that rather than a kernel. Because it's an old version of U-boot, you need to make a U-boot compatible kernel, so you need the make image tool in the next line, and then that is actually off of my Pi. So I've got a U-boot prompt, I tell it to use MMC device, get my kernel image off of the MMC, there's my boot args from like command line.tox, and then the last one runs it. So it's loaded into RAM and it's run. And that's it. Any questions?